Okay, chapter 2. This is all about reasoning and proof. This is a very different chapter for you, dealing with logic. So starting with basic stuff today. 2.1 is about inductive reasoning. Inductive reasoning is using an observed pattern to make a conclusion or a prediction, and that's the examples that we'll go over today. Conjecture is a prediction based on observation. So inductive reasoning is how the reasoning that you're using to come up with a prediction. The conjecture is your prediction. So look at the difference between those two, because you'll see those in your directions. Inductive reasoning is what you use. Conjecture is your conclusion or your prediction. Looking at our first example, it says, use the following example, which is here, to make a conjecture, like a prediction, about adding two positive integers. So this example shows a positive integer plus a positive, positive plus a positive, positive plus a positive. Well, what's the result when we're adding all these examples where we have two positive integers added? We're getting another positive integer. So I'm using this example, and I'm using inductive reasoning, using that example or that pattern to make a prediction of what's going to happen the next time I add two positive integers. Well, my conjecture using this example is that the sum of any two positive integers will be a positive integer. So I'm using this example to say what's going to happen next time. The next time I add two positive integers, I'm expecting to get a positive integer as an answer. To show a conjecture is true, you have to show it's true for all cases. Many times that's not possible. If you think about the example that I just did here, is it possible to show that it's true for every single positive integer? Add all positive integers, all combinations, and show that I get a positive integer. That's impossible. But to show that it's false, we state one counterexample, and this is what I want to concentrate on. Know that if it's true, you have to show it's true for all of them. If it's false, you only need one example. This is a big idea for today. So let's look at some examples here. The directions specifically say, state a counterexample to show that the conjecture is false. So the conjecture is all Blue Ridge Middle School math teachers are male. We know that's false. We only need one example to show that that's not true. And I use myself as an example. So this purple is our counterexample that proves this black statement is false. So Miss Pritz is a Blue Ridge Middle School math teacher, and she is female. This proves that that's false. You could use a lot of different examples, Miss Nicholson, Mrs. Klimek, and any other female math teachers in the building to prove that that statement is false. You only need one. The next one, all prime numbers are odd. So in order to show that this is false, we need to find a prime number that is not odd. If you look at my example, this is our counterexample in purple. 2 is prime, but it's not odd. This counterexample proves that this statement is false. Number 3, the quotient of two whole numbers is a whole number. Quotient is division. So this is saying when you divide two whole numbers, you're going to get a whole number. Well, here's one example. You can come up with lots of examples. These are both whole numbers, and when I divide 9 divided by 2, I don't get a whole number. So as long as you use an example where you don't get a whole number as a division answer, and you're dividing two whole numbers, that's a counterexample. So again, I showed I'm dividing two whole numbers, I get a decimal, that proves this is false. So the big ideas for today is being able to write a counterexample and understand the difference between inductive reasoning and a conjecture. Your homework is posted up here. Remember, you will have a quiz on 2.1 next time, and I'll always answer questions beforehand.